Calculus seems scary. It looks complicated and there's loads of symbols and notations. It feels like an absolute nightmare to look at. But it all comes down to one simple idea, which is how things change. So calculus is split into two different groups. We have differentiation and integration. In this video, I'm going to be talking about differentiation. I'm going to be teaching it from an absolute beginner level, so you don't need any prior knowledge at all. So let's start with a straight line graph, which hopefully you've seen before in school. It takes the form y equals mx plus b, where m and b are just numbers. This means when you get an x value from the x-axis, you plug it into this equation to get the corresponding y value. If you do this for every single x on the x-axis, you get a straight line. So there are two defining properties of a straight line graph, so one of which is the gradient, and that tells us how steep the line is. The second one is the actual position of the graph, so where does the line sit on the axes? So the m number is our gradient. A higher m value means a steeper line. So the way you can think about the numerical m value is for every one step you take in the x direction, how many steps do you take in the y direction? And that's our m value. So let's say we had a gradient of 3. That means if you take one step in the x direction, you take 3 steps in the y direction. So that's a fairly steep line. You could also have a gradient of 0.5, which means if you go one step in the x direction, you only go half a step in the y direction. Your gradient can be positive, negative, it can be fractional, it can be any number. B is called the y-intercept. If we set x equal to 0, in our equation we just get that y equals b. So this tells us that when x equals 0, y equals b. The line passes through the point 0b, or in another way of thinking about it, it intersects the y-axis when the y-coordinate is b. So that's why we call b the y-intercept. We can change b, and that will change the position of the line. We're not changing how steep the line is if m is kept the same. We're just changing where the line sits on the axes. So since calculus is all about how things change, we're very interested in the gradient of a graph. Intuitively, the gradient is all about how the quantities on the x and y axis are changing. If we have a distance time graph, the gradient is telling us how fast the distance is changing over time, and we commonly know this as speed. So how do we find the gradient? A lot of you are probably familiar with rise over run. It's the classic school gradient equation. It means change in y divided by change in x. So you pick 2 points on your straight line graph, you do the difference in the y coordinates divided by the difference in the x coordinates, and that will give you the m value. I'm going to introduce a scary bit of notation now. So this is a delta. It's a Greek letter which means change. So change in y divided by change in x is delta y over delta x. Because we're working with straight line graphs, it doesn't matter which 2 points you pick. The triangle that you form from working out your change in y divided by change in x, they're all going to be proportional to each other, even if you pick a change in x value of 1 or a change in x value of 1,000. When you do the change in y divided by the change in x, it's the same ratio. But what if our graph isn't a straight line? The gradient is no longer constant and it changes based on what point you're analysing. Choosing 2 points and doing our usual change in y divided by change in x actually finds the gradient of something called a secant line. Ideally, we want to be finding the gradient at a specific point. How is the y value changing as x changes in that moment? So this means that we now have to be really careful about what 2 points we pick. Ideally, we want to pick 2 points that are really, really close to each other, because in between those points, we want it so that the gradient doesn't really change. Because if the gradient changes, then we're not really finding the true gradient value, we're finding a secant line gradient. So let's get more general. Let's say we have a graph of y equals f of x. We don't care about the particular equation, it's just a generic graph. Let's say we want to find the gradient at a point that we call x. So our x coordinate is x, and our corresponding y coordinate is f of x, because our graph is y equals f of x. So now we need to choose our second point. So I'm going to say, let's choose a point a distance h away from x. So let's say our next coordinate is x plus h, which means our corresponding y coordinate is f of x plus h. So these are our 2 points, x and x plus h. The smaller h's, the closer our points will be together, and that means that our gradient is more accurate. So how do we get h to be as small as possible? It's time for another bit of horrible notation. So this is a limit. We use limits to analyse behaviour as we approach a value without just substituting the value in. You should know in maths, never divide by 0. It's illegal and people will come after you. It doesn't really work. But what we can do is we can analyse what happens if you were to divide by something approaching 0. So let's take 1 divided by x and ask ourselves what happens as x approaches 0. We are never ever saying what happens when x equals 0, because we know that that's not allowed. But we can say, what happens as x gets smaller and smaller? Well, 1 over x gets larger and larger and larger. So we can quite confidently say that as x approaches 0, 1 over x approaches infinity. It just keeps on getting bigger and bigger. It never actually gets to infinity, it only approaches it. It never reaches infinity because x is never actually equal to 0. It never gets to 0, it only gets close to 0. But we're saying, what does it approach? So as x approaches 0, 1 over x approaches infinity, but it never gets there. So let's go back to our graph. Our change in y is f of x plus h minus f of x, and our change in x is x plus h minus x, and that's just h. So our rise over run is just f of x plus h minus f of x all divided by h. We want to make h as small as possible, so let's take a limit. The smaller h is, the more accurate our gradient is. So intuitively speaking, if h was 0, then our gradient would be 100% accurate. But setting h as 0 doesn't really make any sense. We need 2 different coordinates. If h is equal to 0, we make those 2 points into 1 point. But we need 2, so we can't just set h equal to 0. But what we can do is say, well, what happens to our rise over run as h gets really, really, really small, so as our points get really, really close, and that's why we're using limits. This equation defines differentiation, and yes, I'm actually bringing in the word differentiation finally into this video. So differentiation is the process of finding the derivative of a function, and the derivative is the gradient. Just think about it as the gradient. It's an equation representing the gradient. So you're given a function, you're given a graph, you differentiate it to find the gradient. And this is the equation that we use to find the derivative. This is the differentiation equation. So when we have a graph where the gradient isn't constant and it changes depending on our x value, we differentiate to find a derivative equation which will be in terms of x. So this means that if we're given a function and we want to find the gradient at a point, we take the x coordinate of that point and we substitute it into our derivative equation. So let's take an example. Let's do f of x is equal to x squared. This is a simple quadratic graph. So we're going to want to substitute this into our horrifying looking limits equation. So f of x is just x squared. F of x plus h is x plus h all squared. So our equation has now become the limit as h approaches 0 of x squared minus x plus h all squared, all divided by h. We can't just set h equal to 0 to find this limit because we're dividing by just an h, which means we'd be dividing by 0 and it's not good. So let's expand and simplify and end up with a much nicer equation of 2x minus h. So intuitively just think, as h approaches 0, what does 2x minus h approach? Well, it just approaches 2x, right? So we've solved our equation, and this tells us the derivative of x squared is 2x. So if you want to find the gradient at any point in this graph, you just take the x-coordinate, substitute it into 2x, and that's your gradient. So when x equals 3, the gradient is equal to 6, because it's 2 times 3. We use this equation to find the derivatives of lots of different functions. But the thing is like, it's a bit of a nightmare to have to do that each time. It's a confusing equation, and taking limits can get complicated. There are much easier ways of finding derivatives. There are simple rules and processes that we can just memorize. And one of those is polynomials. So a polynomial equation consists of x's that are put to powers of non-negative whole numbers. So you can have an x squared, an x cubed, an x to the 1,000, and you can even have x to the 0, which anything to the power of 0 is 1. So x to the 0 is just 1. So we can have x squared plus 5x minus 3. We could have 1,000,000 x to the power of 1,000 minus 5x to the 5. That's a polynomial. You can think of infinitely many different types, right? So differentiating a polynomial is very easy. You work with each term at a time. So you kind of separate the terms, you single them out, work with them and put them back into the equation. So you take this power and you multiply the whole term by it. And then you minus 1 from the power itself. And then you're done. So you do that for each term in the polynomial, put it back into the equation, and that's your derivative. So you'll have your original polynomial function, and then you do this process, put it back in, and that's your derivative. So now you've learnt basic differentiation, which is more than a lot of people know.